Assalamualaikum and greetings everyone. We are Group 7 from Session 4 of the EZ 20801 Electronic Engineering Laboratory 2 Lab Control System. We are here to present about Lab Part 3 which is about the Proportional Integrated Derivative PID Control System. Our lecturer is Dr. Ain Binti Nazri. There are 5 member totals in this group which is me, Intana Jiha binti Haidar Tajuddin, Anis binti Abdul Hayu, Hanifah Rana binti Hasbullah, Nur Ifana Jiha binti Abdullah, and Shamina binti Ruslan.
Assalamualaikum warahmatullahi wabarakatuh, and hi, my name is Hanifah Hana binti Hasbullah, metric AE190129. So now I will present for 3.1, which is tabulate the desired outputs. So as you can see here, we have the block parameters, which is speed reference. So we have step time is 1, initial value is 1000, and we have final value is 3500. Next is 3.2, which is P controller. So as you can see here is the block diagram of P controller that I have done in the MATLAB. Next is the controller parameters and performance and robustness for P controller. Here we have the rise time, which is 0.216 seconds, settling time is 1.26 seconds, overshoot, peak, and the others. Next, if you can see here is the result for P controller from PID tuner. So we have the graph as shown here. In this graph, we can find the steady state response, which for P controller, we got the steady state response value is 0.74.
Next, I'm Naifah Najia will explain for PI controller, which is 3.3. So this is the block diagram. So we select the PID controller here. Then we change the controller to PI. Values for proportional and integral. Then okay, so we run it first. Then we tune the PI controller. Then we can see here, this is the graph after we tune it. Then we can update the blocks. Here is the graph for the tune response. So for the graph, we can see that the rise time is 0.378 seconds after tune, and the settling time is 1.9 seconds with maximum overshoot 5.14%. So when we look at the scope, this is the graph. So that's all from me. I will pass to the next member.
Assalamualaikum and greetings. My name is Shamina binti Ruslan, metric number AE190122. I will explain about 3.4, repeating the experiment by using PD controller. In the MATLAB, we can click on the PID controller in the block diagram. And then from there, we can choose the controller that we want. In this case, the PD controller. For this experiment, we will be using the automated tuning. So you'll be using the transfer function base, which is the PID tuner app. And then we can get the result. We can move the slider of the response time or the transient behavior so that we can get the desired response. We can see how the system response would be affected based on the step plot reference tracking graph. We can click on the parameters and then it will show all the important value such as the rise time, settling time, and the overshoot. We click the update block so that the value of the P and D controller will be automatically tuned. And then from there, we will run the model, then click on the scope. Here we can see that the settling time is reduced. There are still overshoots. However, there are still overshoot of the system. That's all from me. Thank you.
We are now at 3.5, which is for the PID controller. First thing we need to do is click here, and the controller is PID. Just click OK, and we run it first. Then we will click here to get the result of the scope. So the next one is for us to do the tuning by clicking the same PID controller, but we need to click the tune. So this is the result once the tuning has been done, but we can slide it to the robust and also for the response to be the faster. in order for us to get the full graph. And we'll click the show parameters to get the value that we want. As you can see here, the rise time is 0.0435 seconds and the settling time is 14.5 seconds and the overshoot is 0%. So that's all from me. I'll pass it to the next member to continue the presentation. Thank you.
For 3.7, discuss and compare all the results above with expected effect. For the experiment with P controller, you can see that there are large overshoot, there are steady state error, and the rise time and the settling time took longer. Large value of this means that it will have a fast response, since the larger the error, the larger the proportional term compensation. However, it leads to instability and the oscillation. Next, for the experiment with PI controller, you can see that the rise time is decreased as well as the steady state error with the addition of I controller. The addition of the integral into the controller is to remove the steady state error caused by the P controller. However, the system is prone to oscillation. For the PD controller, you can see that the settling time is reduced as well as the overshoot. The derivative controller help reduce the settling time, which is why the settling time shown is low. And lastly, the PID controller. It can be observed that the system have reached its optimal state. There are no overshoot, fast rise time, low settling time, and no steady state error. Hence, PID controller provide the most accurate and responsive correction to a control function. Theoretically, the system output should not have oscillation. However, our group were not able to achieve the expected effects. The use of the automatic tuning of the PID controller will make it easier for users to gain the desired response system with optimum performance. That's all from me. Thank you.
Hi, Assalamualaikum warahmatullahi wabarakatuh. My name is Anis binti Abdayu. My metric number is CE190059. So now I'm going to explain part 4, which is the conclusion part, and also the sum up to all the part for these experiments. As everyone knows, a PID controller is a device that regulates a temperature, flow, pressure, speed, and other process variable in this industrial control application. PID controller are the most accurate and stable controller because they are used control loop feedback mechanism to control the process variable. The PID controller can be found by using Laplace transform of equations. And PID controller is also a feedback-based control loop. It's commonly used in industrial control system and other applications that require continuously modulated control. For 4.2, which is the recommendations for the future experiments, in future we as a student hope that the knowledge of the proportional integral derivative, which is PID controller system, guide us when we are working in a big industry that involved with the system, or even in any engineering project. We also hope that by doing this research and development regarding this topic, we are able to develop this field more and gain a lot of knowledge so that we can use when it's needed. We also hope that our lecturer give more tasks like this, because in this experiment we had do a lot of research in Google, and we also communicate with each other of our group member to get more details about this PID control system. The task or duty distribution among member, we work as a teamwork. We divide each other a task that is very fair and square, and everyone be able to deliver the task on time and correctly, preciously. We also discuss among us, which is we use a Google Meet platform to discuss what we don't understand or what we are needed to know, or even if we need any help. So I think these experiments has improved our communication skills in communicate with each other, and also our skills in finding the details and information for this topic. Thank you. That's all from us.